Okay, so previously we focused on descriptive statistics, and now we are going to move more toward inferential statistics. We will start by talking about inferences based on a single sample. So our estimation methods include point estimates and interval estimates. So we're going to talk about both of those today. Basically, we have a population parameter that is unknown, hence why we want to estimate it. This value is our target parameter, and a point estimator of a population parameter is a rule or formula that tells us how to use the sample data to calculate a single number that can be used as an estimate of the target parameter. An interval estimator, or confidence interval, is a formula that tells us how to use the sample data to calculate an interval that estimates that target parameter. So our estimation process involves a population of interest that has an unknown mean. We take a random sample from that population and find a point estimate for that mean. Here it is, x bar equals 50. Then we can calculate a confidence interval to tell us how confident we are in that estimate. The key elements of interval estimation are that we have an upper and lower bound to our interval and that the mean is in that interval. A confidence interval provides a range of plausible values for the population parameter that we're interested in. So according to the central limit theorem, which we've talked about several times at this point, the sampling distribution of the sample mean is approximately normal for large samples. So let us calculate the interval estimator, our sample mean x bar, plus or minus that times the standard deviation. So here we use 1.96, which is the number of standard deviations for a 95% confidence interval. I would remember 1.96 because we use that number a lot. So prior to drawing the sample, what are the chances that the interval will enclose mu, the population mean? So if our confidence level is 95%, then in the long run, 95% of our confidence intervals will contain mu, the true population mean, and 5% will not. So for a confidence coefficient of 95%, the area in the two tails is 0.05. So to choose a different confidence coefficient, we increase or decrease that area, called alpha, assigned to the tails. If we place alpha divided by 2 in each tail, and z alpha divided by 2 is the z value, the confidence interval with coefficient 1 minus alpha is. So what we have is this normal table from the normal distribution that we've been talking about, and we divide our alpha between those two tails. So that's why it's alpha divided by 2. And that will give us our z-score, so that we need to calculate out for our confidence interval. So for 95%, we want to find alpha. So we say 1 minus 95% leaves us at 5%. So we have 5% in the two tails combined. So we have to do alpha divided by 2 to find the one side. So that's why it's alpha divided by 2. So we take that 5%, we divide it by 2, and now we have 2.5%. And using a decimal, that would be 0.025. So this is going to be important to remember because we're going to take that value onto a normal table and look up the value to pull back to get our z-score. And it just happens that 95% z-score is 1.96, which is where that number came from on the previous slide. So a few conditions are required for so we have to have a valid large sample confidence interval for mu. So the first is it has to be a random sample and selected from the target population. The second is the sample size n has to be large. In general, in statistics, that is larger than 30. Due to the central limit theorem, this condition guarantees that the sampling distribution of x bar is approximately normal. Also, for large n, S will be a good estimator of the standard deviation sigma. So, like we've said before, because of the central limit theorem and law of large numbers, all sampling distributions will converge to the normal distribution, and hence why we can estimate in this method and how statistics works in general. So, assuming we have a large sample, we can use this formula to estimate the confidence interval. If our sample size is larger than 30, then we can estimate the standard deviation with the standard error, which is just the sample standard deviation divided by the square root of the sample size. So to create the confidence interval, we need to multiply the z alpha divided by 2 by the standard error. We have sample size n and the standard deviation. We can find the confidence level in Excel. So Excel provides a formula for finding the confidence interval based on a z-score and the normal distribution. So let's say you're interested in a 90% confidence interval. Well, to find alpha, it's 1 minus 90%. So 0.1 is 10%. So that gives us our alpha value that we need for our formula. Well, given a standard deviation of 0.05, sample size of 100, and a sample mean of 1.99, then we use this to calculate out the confidence level, and then we can add and subtract that value to get our confidence interval. So the lower is going to be our mean minus our confidence level, and the upper bound will be our mean x bar plus our confidence level. So here is an example. You are a QC inspector for Gallo, a cheap wine company. The S, or sample standard deviation, for 2-liter bottles is 0.05 liters. A random sample of 100 bottles showed that X is equal to 1.99 liters. So our X bar, or sample mean, is 1.99. Then it asks, what is the 90% confidence interval estimate for the true mean amount in the 2-liter bottles? So that's what we have here. So the confidence interval of interest was 90%. So you subtract 1 minus 90% to get 10%, and that's our alpha. Standard deviation was 0.05. Our sample size is 100, and our sample mean x bar is 1.99. So we use that in our confidence interval formula. So our confidence level is 0.008. So we subtract that from our sample mean, and we add it to our sample mean, and then that's how we get our confidence interval. So if you wanted to do it manually, this is how you would put in the formula. So for a 90% confidence interval, our z alpha 2 is going to be 1.645. That is another number you probably should remember, because it's one we use pretty commonly. We take our standard deviation and we divide it by our square root of our sample size, and then we subtract it from our sample mean. So we got 1.982, which is the same as this that we got using the Excel formula. It's just been rounded. So on the other side, or the upper bound, we do the same thing. We have our sample mean. We add our Z alpha 2 pulled from the normal table, which is 1.645. We multiply it by the standard deviation divided by the square root of our sample size, but using our formulas, we can get the same value, 1.998. Now, if we have a small sample size, then we have to use a different table. It's called a t-table. So we can't use the normal table for instances where our sample size is below 30. So this is how we can account for the smaller sample size. Basically, if our true standard deviation sigma is unknown, we have to estimate it from our sample. So when we adjust for our t statistic in Z, we know, or we have a good idea of what the true population is, but we have to estimate it with we have to estimate the standard deviation for using to find our t statistic. So the t statistic has a sampling distribution very much like that of the z statistic. It is mound-shaped, symmetric, and has a mean of 0. The primary difference between the sampling distributions of t and z is that the t statistic is more variable than the z statistic. So what we will find is that the t distribution is going to have to be adjusted by the degrees of freedom. So the actual amount of variability in the sampling distribution of t depends on the sampling size n. A convenient way of expressing this dependence is to say that the t statistic has n-1 degrees of freedom. So here is how the shape of that distribution changes depending on the number of degrees of freedom. So lower sample sizes and lower degrees of freedom, we end up with a more flatter distribution, and our tails are kind of, long and flat. But as our sample size increases and our degrees of freedom increases, we can see that the tail becomes higher and smaller, so we're going to be able to fit more area in a smaller section of the tail. And then this one is the normal distribution, and we can see that as the sample size increases and our degrees of freedom increase, we approach the normal distribution. And thus, generally, once you have a sample size of higher than 30, you can use a z-score and the normal distribution. So to read a t-table, we'll have to use our t-table and our degrees of freedom to get our t value. So let's say you have a sample size of 5, then that would be n-1 degrees of freedom, so we'd have 4. And then for alpha, and this particular one, alpha is 0.025, we would get our t statistic of 2.776. So if we want the t value with an area of 0.025 to its right and 4 degrees of freedom, we look in the table under the column t 0.025 for the entry in the row corresponding to degrees of freedom. So this entry is t 0.025 is equal to 2.776, and the corresponding standard normal z-score for z 0.025 equals 1.96. So previously, when we were talking about it, we said, for 95% confidence level, that'll give us an alpha of 0.05, and then 0.05 divided by 2 is 0.025. So that's how we get the same equivalent of 1.96 is the same as the t.025 for 2.776. So they're just drawn from different tables and different distributions. Basically, to account for the smaller sample size, we're giving ourselves less area in the tail. So that'll come into more important as we move through inferential statistics. So for a small sample confidence interval, we have to find the t alpha divided by 2 to obtain the confidence level. So only a slight variation from our z-table version or a larger sample size. So conditions required for a valid small sample confidence interval for mu is we need a random sample that is selected from the target population, and the population has a relative frequency distribution that is approximately normal. So let's take a look at an example using a sample size of 25 with a standard deviation of 8 and sample mean of 50. We can use Excel for this as well with the confidence.t function. Remember that alpha is 1 minus the confidence interval we are interested in. So this is how you would solve it manually using the formula. But like I said, we can use Excel. Let's see. So alpha is 1, we were interested in 95%. So 1 minus 90.95 is 0.05, so it's 5%. We have a standard deviation of 8, a sample size of 25, and we're interested in this X bar sample mean of 50. So the only difference to our formula is confidence.t to adjust for our lower sample size. Since we don't have a sample size of 30 or higher, we have to use this other function. So that gives us our confidence level that we can subtract from our mean. So you can see that our lower bound is our mean minus our confidence level, and our upper bound is our mean X bar plus our confidence level. And it gives us these same values, and that way you don't have to manually calculate it out. Okay, so for a proportional sampling distribution, the mean of the sampling distribution of p hat is p. That is, p hat is an unbiased estimator of p. Standard deviation of p hat is found by the square root of p times q divided by the sample size n, where q is equal to 1 minus p. For large samples, we need at least 30 samples, where half represent p and the other half represent q. So we need 15 of each. So very similarly to our confidence interval for our mean, our confidence interval for a proportion p hat is to add and subtract the z alpha divided by 2 times its standard deviation. And remember, to find the standard deviation of a proportion, we take the square root of p times q divided by n, our sample size. So when dealing with proportions, there is not a built-in Excel function, so it will take a little more manipulation than usual. Here, we will need to write the formulas to manually calculate out the values. So what I did for finding z p hat confidence interval, we have let's modify it. So we have a sample size of 400. We have 32 of those 400, and we are interested in 95% confidence interval. So we have a sample size of 400. Confidence interval of interest is 95%. So we find the z alpha 2, so we subtract the alpha from 1 and we divide by 2. We need that. We calculate our standard deviation, which is the square root of p times q divided by the sample size. Then we have to look up our confidence level. So we're going to use Norm's inverse of B3, which is 0.025, which will give us our value of 1.96. And then we multiply that by our standard deviation. That will give us our confidence level that we can then subtract from our p. So p of 0.08 minus our confidence level gives us the lower bound for that confidence interval, and p of 0.08 plus our confidence level gives us the upper bound. So that's how we can find the confidence level. So not quite as simple as using just a single formula for doing it with a proportion. Let's do a second example to see how this works. So you're a production manager for a newspaper. You want to find the percent defective of 200 newspapers. 35 had defects. So what is the 90% confidence interval estimate of the population proportion defective? So we have a sample size of 200. Interested in the 90% confidence interval. We have 35 defective out of 200. We find that our confidence level is 0.04. We subtract that from our p of 0.175, get 0.13 to 0.21. Okay. So in general, we express the reliability associated with the confidence interval for the population mean mu by specifying the sampling error within which we want to estimate our sample mean. So with 100 times 1 minus alpha percent confidence. Sampling error, denoted here as SE, then is equal to the half width of that confidence interval. So that's important when we want to calculate out a sample size. Let's say we were going to do a survey and we needed to know sample size for whatever we were trying to survey for in order to get a particular level of confidence. So in order to estimate our population mean mu, we need a certain sample size to account for our standard error. To find that sample size, we use the formula given here. Our sample size N can be found by multiplying our z alpha divided by 2 by the population standard deviation. We square both of those and then divide by the standard error squared. I find that generally finding an online calculator will work best for these problems, but I'll try to show you how to do it in Excel anyways. So what sample size is needed to be 90% confident the mean is within plus or minus 5? So a pilot study suggested that the standard deviation of the population is 45. So we're going to have to do some manual tweaking in Excel to make this work. So we're interested in 90% confidence interval or confidence level. Our standard error was plus or minus 5. because of the pilot study, we know that the standard deviation for the population is 45. We use this formula here to find, we need our alpha, so that's 1 minus b1 divided by 2. So we need our z alpha 2 is going to be 1 minus 0.9, which is 0.1. We divide that by 2 to get 0.05. And that gives us a z alpha 2 of 1.64 drawn from the normal table. Then we use our formula of our z alpha 2 squared times our standard deviation squared divided by our standard error squared of 5. It'll give us 219.14. We have to round it up to a whole number, and that's how we get 220. So, same idea there. So, in order to estimate P with a sampling error of SE and with 100 times 1 minus alpha % confidence, the required sample size is found by solving the following equation for N. So it is very similar to the last formula, except that standard deviation is replaced with P times Q. So to find the standard error, it was the square root of PQ divided by N, but since we're going to square it, we can remove the square root, so that's why we don't square that proportion. So let's say we want a sample size is needed. So we want to find out what sample size is needed to estimate P within 0.03 with 90% confidence. So we need the half width of our standard error, so 0.03 divided by 2 is 0.015. We need z alpha 2 for our 90%. We know that we just found that out to be 1.645. We weren't given a P or a Q, so we'll just say it's 50-50. So it's 0.5 times 0.5, and we'll divide by the square of the half width of the standard error. So we can do this in Excel as well. So sample size for a proportion. We're interested in 90% confidence. We have a standard error of 0.03. Half width of that standard error is 0.015. We weren't given a p-value or a value for our proportion, so we're going to use 0.5 to estimate. So p q is 1 minus p, so it's also 0.5. Our p times q is 0.25. So we pull the z alpha 2 value the same way from our normal table. We use the formula to calculate it out, and we get 3006.15, but we have to round up, so we get 3007. So the same value as just using the manual formula. So that's all for today, and we'll talk more and do some more examples later on.